Time Varying Fields, Retarded Potentials, series on Electromagnetic Field Theory, lecture number 3.30. Retarded potentials are potential functions defined for use with dynamic fields. In dynamic fields or time varying fields, there exists electric field, there exists magnetic field too. With respect to electric field, one can define the scalar potential function. With respect to magnetic field, the vector potential function can be defined as done in case of static fields. These potential functions defined for dynamic fields, there exists a delay in their expressions. Another synonym for delay is retardation. So potential functions that are defined for dynamic fields, they carry delay, retardation in their expressions. For this reason, they are called retarded potentials. Now we move further to explore the field of retarded potentials. In general, to find the field intensity due to an arbitrary source distribution, two possibilities are there. One is single step method. Here fields are calculated from the source distributions, but it requires relations connecting the source directly with the fields. The second method is a two-step procedure. Here, first potentials are calculated from the source distribution, and then from potential fields are computed. The second method is usually resorted to when the relations directly connecting the source and fields are not available. In case of static fields, we have relations. For example, field intensity E is 1 by 4 pi epsilon integral rho d tau by r square r cap. So here this is source, this is field, relation is available. Similarly, Biot-Savart law in magnetic fields gives us a relation connecting source with field intensity. So as far as static fields are concerned, relations are available connecting source with field. But in case of dynamic fields, it is not so. Dynamic fields, we know they are created by AC. So everywhere dynamic field, if you consider a point, here exists E, here exists H, but we don't have relations connecting E with current or H with current. So first method or single step method is not possible in case of dynamic fields. The second method is usually resorted to when the relations directly connecting the source with the fields are not available, or when there is a computational difficulty in evaluating the fields due to first method. See, in case of time varying fields, relations connecting the source distribution with the fields directly are not available. Hence, we go to second method, two-step procedure. Retarded potentials are potential functions defined for time varying fields. As already mentioned, retarded potentials are defined potential functions for use with dynamic fields. They are connected to sources on one side and fields on the other side. So what happened is we have relations for potential functions connecting them directly with the sources. So potential function, when source distribution is given, potential can be computed. Potential functions are directly connected to fields. Relations are there connecting them with the fields. So on one side they are connected to sources, on the other side directly they are connected to the fields. So normally in dynamic fields what we do is from given source distribution we first compute potential, from potential then we do field calculations. Wire antennas are the earliest antennas used by mankind, and in the analysis of these antennas, retarded potentials are widely used. While studying radiation, you find the benefit of retarded potentials in the analysis of wire antennas. Now, a small brief on dynamic fields. Reason is retarded potentials pertain to dynamic fields. Surrounding AC or accelerating charge carrying conductors, dynamic fields exist. The AC and its associated accelerating charge are interconnected by continuity equation. In dynamic fields, both electric and magnetic fields interlinked to each other exists. The interrelation between the fields is governed by Faraday's law and Ampere's law. With respect to electric field, scalar potential can be defined, and with respect to magnetic field, a vector potential can be defined similar to static fields situation. Now, let us spend a few moments on first point. What is this first point? First point. Dynamic fields are sourced by AC. Here is a conductor. It is carrying AC. Surrounding this, we have dynamic fields. Here, everywhere, E and H exists. Now, AC, alternating current. This is current. We all know current is flow of charge. So AC is associated with some charge. Charge and current, these are related. That relation is provided by continuity equation. In fact, it is in one form. It is del dot J equal to, or divergence of current density is minus dou rho by dou T. On one side current, on the other side charge density. This aspect is quite important. Reason is, normally E is connected with the charge density and H is connected with current. But charge and current are related. Charge and current are related through continuity equation, of course. Therefore, one can conclude that E and H also must be related in the dynamic fields. The relation between E and H is provided by Faraday's law and Ampere-Maxwell's law. That is second. With respect to electric field, here electric field exists. With respect to electric field, a scalar potential can be defined. With respect to magnetic field, a vector potential can be defined as rho and J are related, E and H are related. As E and H are related, potentials also must have a relation between them. Of course, that relation is called Gauss relation or Gauss relation. So we are going to discuss all those things in the present session itself. Potential functions formulated for time varying fields are called retarded potentials. Their distinguishing and differentiating feature from static potential functions is incorporation of delay. Retardation and delay, these are synonyms. So retardation is there in their structure. That's why those functions are called retarded potentials. In dynamic fields, wave exists and a disturbance at a point takes time or delay to reach other points due to finite propagation velocity of the wave. So here in these last two paras, what he's trying to tell is why retardation or why delay is incorporated in the potential functions. Why? What is the reason? Reason is this. In dynamic fields, wave exists. Wave means traveling with some velocity. This velocity is not infinity. It is finite. Finite velocity means it implies a disturbance to reach from one point to another point. It takes some time. Some delay exists. That delay is incorporated in the functions of the retarded potentials. That's why they are called retarded potentials. By introducing time delay or retardation in the potential function formulation, the presence of wave with finite velocity in the dynamic fields is taken into account. See, in static fields, no wave, so hence there is no question of any delay. But in dynamic fields, wave is there, delay is there. Therefore, here we have to incorporate. There is no wave, no delay, therefore no delay in ordinary potentials or potential functions that are defined with respect to static fields. Here some expression is given. A vector potential function in time varying fields is defined as A or T is mu by 4 pi integral J r cap T minus r by V by r d tau prime. This is time domain. Time domain. Why reason is T is there. Time domain. This is phasor domain relation. Time is absent. T is absent. Similarly, a scalar function in time varying fields is defined. For time varying fields, it is defined like this. You see here, vector potential function is defined with respect to J, whereas scalar potential function used rho. Don't think this rho is different from J. Rho and J are refers to the same source. They refer to the same source. What is this rho? Del dot J equal to minus dou rho by dou T. That connecting relation, whatever rho is there, that rho here he is using. Right. This is time domain relation, whereas second one is, this one is phasor domain relation. Now, first one or two points I want you to notice. There is very little difference between the function. First one, let us consider vector potential function in time domain. This function with the vector potential function which we have for steady magnetic fields. Very little difference. Only difference is here T has come into being. In this expression, T has come into being, and current that is used in the defining relation is delayed current. It is retarded current, delayed current. Time is also there, but it is retarded by certain amount. So structure wise, the relation is there also. In case of steady fields also, it is inversely proportional to distance, proportional to current configuration and all that. It is dependent upon permeability. 1 by 4 pi is the proportion. So all those things are common, except that time is there. First thing is time is there in the present expression and delayed time on the right hand side. Similarly, when it comes to scalar potential function, this is very much similar to the scalar function which we have in case of static electric fields. Of course, difference is t. It has become function of time because it is to be valid for dynamic fields. Dynamic fields are functions of time. Therefore, when it is defined for dynamic fields, this also must be a dynamic one. Therefore, t is there. Now, charge is retarded charge, delayed charge, t minus r by v. Of course, when you convert this time domain into phasor domain, this delay, it has become a factor, a phase delay. Actually, this represents a certain amount of phase. Here also phase. Okay. Now, one or 2 points regarding this small r, capital R, and all that. Capital R is there, but what is this small r and all that? Let us suppose some current source is there, certain current. J is flowing through this. J is flowing through this. Of course, this J is related to rho through del dot J equal to minus dou rho by dou. Okay. So when I say J is there, I mean rho also is there. Okay. It is time varying or it is AC. Now I want potential somewhere here. Let us say at a point P, I want potential. How it is defined or how it is calculated? Let us suppose the position vector of point P is, normally it is indicated by R prime. Position vector. Position vector of source point. Here we consider a differential volume and it becomes source point. Source point. Position vector of source point is indicated by R. R bar means it is a vector. Bar indicates a vector. So this is a vector R, this one, whereas R prime is this one. Now if you connect these 2 points, source point with a field point, you have another vector. Here I have to indicate directions. I have to give directions to R prime as well as R. I am giving directions. Now if you connect source point to field point, then you are with another vector. This vector is usually indicated by capital R. Capital R. Magnitude of this capital R is indicated by simply okay. Now you have some idea regarding R. R is position vector of the field point. R prime is position vector of the source point. Capital R is the distance between source point and field point. V is velocity of the wave. This is all, this situation, this configuration is all, it is located in dynamic field. In the dynamic field, wave exists. Wave means traveling with certain velocity. V refers to that velocity. In general, this I can say velocity is 1 by root mu epsilon. The same thing applies to this also. Notice this is vector potential, this is scalar potential, and these are integral relations. Integration is there. That's why integral relations. These integral relations can be converted into differential relations also. When you convert them into differential relations, you will be getting del square A equal to minus mu epsilon dou square A by dou t square minus mu J. This is time domain relation, whereas bottom one is phasor domain. Similarly, scalar function can be converted into differential form. It becomes del square V minus mu epsilon dou square V by dou t square equal to minus rho by epsilon. This is time domain. It can be converted into phasor domain. Here I want to mention an important point. Conversion from time domain to different phasor domain is not a great thing. Just to replace dou by dou t with j omega. That's all. Dou by dou t with j omega. Then the equation gets converted into phasor domain. Of course, when in phasor domain, the potentials or fields, sources all become independent of time. Now, the vector potential relation with field in both time and phasor domains is mu h equal to del cross A. As already mentioned, potentials are connected with the source on one side. They are also connected with the fields on the other side. That is their beauty. Because of this double connection, we are able to use them to compute fields. From sources, first we compute potentials. From potentials, we compute to fields. What is the relation that is existing between potential and field? Till now we have expressions connecting sources with fields, sources with potentials. Now it is the turn of relation between potential with field. So field mu h is del cross A. Actually, this mu H equal to del cross A, this relation we have already studied while studying steady magnetic fields. So that relation, same relation has been imported into dynamic fields also, because it is found valid even in case of dynamic fields also. So this relation is not new. You need not to do any modification for the steady magnetic field relation. Therefore, they found it quite suitable for use with the dynamic fields also, and hence they imported. Now B equal to del cross A is the relation between magnetic potential and magnetic field. Of course, B equal to mu H. Right. Now, here I am showing another relation. This relation connects potential with field, electric field. E equal to minus grad V. This is the relation which we come across in electrostatics. This relation as it is not valid for dynamic fields. So certain modification has been done. That modification is subtracting dou A by dou T. So E equal to minus grad V minus dou A by dou T is the electric field in terms of potentials. This is in time domain. Of course, we can convert it into phasor domain easily. As already mentioned, charge is related to current. The relation is given by continuity equation. Fields are related. Electric field is related to magnetic field. Their relation is given by Maxwell's third equations, that is Ampere's law and Faraday's law. Potentials are also related. Retarded potentials. Magnetic vector potential, retarded potential is related to scalar electric retarded potential. Their relation is called Gauss relations. Gausses provide the connection between scalar and vector retarded potentials. There are two Gausses. One is called Lagrange Gauss, another is Coulomb Gauss. Before going further, I want to state the basic difference between Lagrange Gauss and Coulomb Gauss. Lagrange Gauss, it obeys relativity. Coulomb Gauss, no, it doesn't take into account relativity. So Lagrange Gauss is realistic. Of course, Coulomb Gauss is simple. What is Lagrange Gauss? Del dot A equal to minus mu epsilon dou V by dou T. Here on one side we have vector potential, on the other side we have scalar potential. This is the connecting relation between vector and scalar potentials in dynamic fields. It is called Lagrange Gauss. So this can be put in phasor form by replacing dou by dou T with j omega. While studying retarded potentials, we also come across a vector. It is called Hertzian vector. What is this Hertzian vector? Hertzian vector is defined from or with respect to vector potential A. Z is 1 by root mu epsilon A dot dt. Using this vector Z, one can find E del grad div Z dot mu epsilon dou Z by dou T and H epsilon third dou Z by dou T. The significance of Hertzian vector is, see, when we use A, magnetic vector potential, V, scalar potential, to find fields, electric field and magnetic field, we require both the potentials. We require A, we require V. For example, to calculate E is minus grad V minus dou A by dou T. So to compute A, we need V, we need A also. So two quantities are required to be computed. But if you go for Z, using this single Z, you can compute E, you can compute H also. See, E is in terms of Z. H is also in terms of Z. That's what he's telling. The significance of Hertzian vector Z is a single function is sufficient to compute the fields, whereas via potential route, two functions are required to find the fields. Here all the relations so far shown, they are all enumerated in a tabular form for ready reference. This is Gauss transformation, Coulomb Gauss, Lagrange Gauss. This is time domain, this is phasor domain, Coulomb Gauss and all that. These relations I have already stated. Charge and current, they are connected by continuity equation. Electric field and magnetic field through Maxwell's curl equation. Electric potential, magnetic potential, these are connected through Gauss transformations. This is what I want to share regarding retarded potentials for now.